Yeah, let's now analyze this coefficient comparison. What do we have? We have equations with some parameters. One parameter is Tn, the other is Tv. Tn and Tv are fixed, unknown, because they are set with pole compensation to the process time constant, so they are not anymore free. No choice, no change is possible or sensible. What do we have more? Then we have Kc. Let's look for K. K without index is a process gain. It's also given, measured or not, defined, calculated. K is known, given, unchangeable. Then we have Kc, the controller gain, which is free, and step depth, the controller step depth, which is free. So we have two free parameters. And with these equations, two equations, you can calculate what happens with the damping factor and the omega naught factor with given Kc and step depths. But that is not that what really helps. Better is if we use these equations to select a damping factor and a natural frequency, and then calculate the relevant Kc and step depth value. That's behind the controller design. Yeah, so we want to have a behavior and then calculate the settings, the parameters of the controller. That is a real, true controller design idea. The question is only, is a damping factor and more than the natural frequency a real good practical parameter to discuss with the customer, with the user? I think not, because normally the user is not informed what is a PT2, what is a damping factor, what is the natural frequency of a PT2. So better we discuss the situation with the step response of a closed loop system, because this step response can be discussed with any human being who has some intelligence, with the types, with business people who defines products and so on. A reference step response can be discussed with not engineering people. And the damping factor and the overshoot can be defined with the tolerance range, so this can be discussed. And the speed node, the first maximum of the step response of a PT2 is also well known as Tm value, and this can be calculated very easily with PT2 equations. And the Tm is a good indicator of time. If this is minutes or hours or seconds, any normal human being can understand, get a feeling of the speed of his closed loop system. So what I recommend is the following. I make a table and say, okay, the closed loop system has a damping, which is selectable, is free, and a speed, which is selectable. And you can choose any value for this. These are the both free parameters with which we can define the damping and the speed. The damping with customers can be discussed with the overshoot or tolerance range. The speed can be discussed with the Tm value. This is what is helpful for the user. With our knowledge, now we convert this into PT2 equations, PT2 parameters. We know the U factor can be converted into a D factor with the equation above. Don't want to make the copy of this equation. The equation here, this blue equation. There is a strong relation between a damping factor and U factor. So the user selects the U, you calculate this into a D value, and here this can be selected or calculated into an omega naught value with the PT2 equation. I just make a copy of this. Look into workbook, page 22. Here the equation Tm calculates out of omega naught using damping factor, but this equation can easily be solved to omega naught. Put omega naught to that position, put Tm to that position, and then we have the final solution, the final expression we use here. Omega naught is pi divided by Tm multiplied with 1 minus d squared. So if user has selected a Tm value, with this equation we can calculate the omega naught, the PT2 parameter omega naught, and now this can be selected into a step depth and a Kc value, so that you can realize the PID T1 controller. Realizing PID T1. And if you have Kc and step depths, then of course you can calculate the R1, R2, R3, C1, C2. Yeah. So with the PID T1 equations, you can select now the 3 resistors and 2 capacitors, and then build it up, test it, and be happy with this. What is missing now is equations for Kc and step depths out of this both equations. That is the next step I will do here on this paper. Yeah, we need an equation. Kc is a function of d and omega naught. Step depth is a function of d and omega naught, and then we are ready. And exactly this can be gained with the using of these 2 coefficient comparison equations. Okay, I have 2 equations, 1 and 2. The first equation I solve to omega naught. Omega naught is omega naught on the left side is 2d divided by Tn multiplied with Kck. So then I use equation 2, solve for Kc. Kc, this on the right side, omega naught on the left side gives Tn Tv times omega naught squared Kc divided by step depth times K. Okay. Now I set omega naught into this equation. With 1 I get Tn Tv divided by step depth divided by K. It's multiplied with the square of omega naught is 4d squared Kc squared K squared divided by Tn squared. Now I can reduce 1 Tn. I can reduce 1 K. And you see on both sides now I have a Kc. I want to solve now this equation to Kc. Here's a Kc squared and here's a Kc. So finally we divide this and this factor by Kc. We get 1 on the left side is on the right side Tv times 4d squared times Kc, 1 times K divided by step depth times Tn, and I solve this to Kc, gives that expression I want to use later. Now this is the first resulting equation I want to use to design my controller. Kc and all the other parts on the other side. So Kc is step depth times Tn divided by Tv times 4d squared times process gain. This is Kc. Okay, you see Kc and step depths Casey uses the step depth, so we need a second equation for the step depth, which comes now in the next step. I call this equation 3. Equation 3 is one result. Now I put equation 3 into equation 1. 3 in 1 gives omega naught is 2d divided by Tn times k. So times Kc. Now I replace Kc with step depth times Tn divided by Tv times 4d squared k. And you see what happens. Now the Tn can be reduced, the k can be reduced, the 2d can be reduced against 4d squared. This gives 2d. So finally we have here the following equation. Omega naught is step depth divided by 2 times d times Tv, and that's all. Or that's equation 4, we can say. Or we solve to step depths. Step depth is omega naught divided by 2d Tv. So very simple relation. Step depth and omega naught are linear. So we can say with this equation and this equation, you can do the following design very simply in the following way. Note that you know the d and the omega naught factor. With omega naught and d, you calculate step depths, put this step depths here, and with the step depths given Tn and Tv and 4d squared and k, calculate Kc. So with given damping and speed value with this equation, you can calculate the parameter value of the PIDT1, set these parameters in your digital software, or calculate the resistances and capacitance, and then the controller is designed. Yeah, with 3 and 4, calculate Kc and step depths with given the damping factor and omega naught factor. Often, note, not Tm or omega naught are selected, but step depths. So we will do this later. Try step depth is 1. What happens? What is this? Step depth is 1. PIDT1 moves into a simple PI. So this design also gives the PI design. Set just step depth value to 1, and then these equations are just PI design equations. Then if this is not fast enough, try step depth 2, step depth 5, maximum step depth 10. Then I will show you try if realizable. You have to know that the larger the step depth, the larger the speed. The step depth value is a direct, here you see this, the omega naught is proportional to step depth. That means if omega naught is proportional to step depth, Tm is inverse proportional to omega naught. So if step depth is doubled, Tm is divided by 2. So step depth is a real speed parameter. The larger step depth, the smaller Tm. The larger step depth, the larger the speed. Yeah, step depth is a really speed parameter. And if you increase the speed parameter, you should know this also increases the actuator peaks. And the speed is only realizable if the actuator can amplify this peak impulse and give it to the process. Otherwise, the step depth values are not realizable. try if realizable with checking. We will do this in a real example with checking the actuator peak values. Okay, so far this is the theory of the flash design. We end up in 3 simple equations, and these simple equations can be found in the workbook on page 33. Look for this. The flash design is defined here. Note that the open loop is just an IT1 in all cases. We have just worked through the line number 25, the combination of a PIDT1 with 2PT1. This is also included 2.3, special case 2.5 with step depth 1. So we have already shown 2.3, but 2.1 and 2 and 4 are different combinations where you can do the same steps and read here the resulting equations. Now this equation, now this is the PID transfer function, process transfer function, resulting controller design. If you have this type of controller, a PDT1 controller, and this process, IT1 process, note I have given here the both controller design equations here on this page. 2.3 is this line with step depth 1. 2.2 is I controller with PT1 process. Look for these equations. Here we have a P controller with an IT1 process. Look for these equations. Note that in all 5 cases, the closed loop system behaves exactly like the PT2 behavior, where the case 1 and damping factor and natural frequency are the speed and damping parameters as discussed before. Note that this design is also available as a tool program in my WinDF C# tool. I just want to show you in the next step. Very simple. Go to Tool Programme or go to my personal homepage www.jörgbayerlein.de, and there you can find during menu, go to C# projects and look for the WinDF C# project. I started and show you that the 2.5 equation is realized as a simple tool module. Yeah, I start WinDF C#. Look for controller design, and here look for this flash design 2PT1 point. Here you get this window. Type in the 3 given process parameters and then click on any other input field. Here you can define the damping either with given damping factor or with given overshoot factor, or with given phase margin value. Phase margin comes later in chapter 5. It's not defined yet, but of course a damping parameter. And here you can define the speed parameter either as step depth value or natural frequency value or KC value. Note this K is the controller gain. Or you can define the Tmax value, or you can define the product of controller gain times step depth. This is an indicator for the peak value. If you have selected one of the damping parameters and one of the speed parameters, the program applies pole compensation. Tn and Tv are then selected to the both process time constants, and the program calculates in Kr value. So if you change, for example, if you say, no, I have a 5% tolerance range, go here, go to another field, and automatically the program calculates the new controller gain value. If you say, okay, I want to be ready after 1 second, type your second and leave this field by clicking on another field. Then you see use this controller gain, the step depth value, and realize your system with these resistors and capacitance. Note that the three gray fields are only calculated, not changeable. Here you can select C2 or R1. That's your design. If you say, okay, I have not a 3.1795 microfarad capacitor, I have a 4.7 microfarad, then automatically type this in, and then the program calculates the other four parameters. So I think this is a useful tool. Now you know the background of this tool, that is the theory of the flash design, and the rest is simply behind this program. I use that equations I have shown you in this video.